Good afternoon. Welcome to Krishna's classroom. With the last episode, we completed a quick review of the Lebesgue integral theory. Now we are going ahead further to generalize these ideas if it is possible. Okay, what are the things to be generalized? So now if you just recall, you can see that it is from the concept of length of an interval that you generalized to the concept of Lebesgue measure of measurable sets. Because not all sets are measurable on R, but so we were working exclusively on R, and not all subsets are measurable in the sense of the Lebesgue, the way in which we have defined it, and otherwise all intervals are measurable. And for intervals, the Lebesgue measure coincides with what is called the length of the interval. Our next step is to seek a generalization of the integration theory, the entire integration theory that is possible. So we have to prepare the ground. We have to go from the concept of Lebesgue measure to a concept of measure, new concept of measure. Okay, that is one thing. Also, one of the things that you would like to do is to go to a general setting, namely instead of working on the real line R, you would like to generalize it to more general sets. Okay, say an arbitrary set on which is it possible to introduce the concept of a measure. Okay, now this is our objective. So that eventually your Lebesgue measure should be a very special case of what we are trying to do. And in fact, you see that there have been compulsions from the probabilists to get a well developed theory for taking care of all the aspects of probability theory. Now, in this context, they came across the necessity to develop the concept of integration. So that is one reason which provoked questions of this kind. As far as analysts are concerned, they want to develop integration theory on R, on possibly Rn, on possibly C, with other structures to go with it, and Cn, or more generally to take it further to Banach spaces, and so on. I mean, there are all sorts of possibilities that you can have. But to achieve our task, we'll just recall what exactly is a measurable set and what exactly are the measurable functions. As we have constructed in the case of Lebesgue integral. Now you see that what is the structure of Lebesgue measurable? See, we work with R. There we have the Lebesgue measurable sets. Let me just designate it by M. Lebesgue measurable sets. What are the characteristic features of Lebesgue measurable sets? They are subsets of, so the Lebesgue measurable set is a subcollection of the set of all subsets of R. That is the first thing that you observe. It's certain features. What are the features that you have? See that the whole of R belongs to M. Then if A belongs to M, then A complement belongs to M. And finally, if An is a countable sequence of sets which is contained in M, then union that means the measurable class of subsets of R have the property that R is an element of that, A belongs to M, then A complement is in M, and if a collection An belongs to M, then their countable union also belongs to M. Now these are the three features. Apart from that, we have some more things like if you we are working on R there are other structures. So as far as this is concerned, we are not using any special features of the real line, because real line has a lot of structures on it. For instance, you have it's a field. Set of real numbers is a field. Set of real numbers appear to be what you call a vector space of dimension 1 over R, and so on. And so see, there are a lot of other structures that you go with it. And then you have what is called the if you take an interval and translate it, you get an interval. And you see that this An may not be an interval. It can be some subset of it. Okay. So there are other features. The translate. But that essentially uses the other structures of the real line. Okay. So if you are seeking a generalization for making or imposing a structure of this kind, you don't need any other structure of the set. So what we start with is this. Let us indulge in our generalization. So we start with X, a set of objects with no structures assumed on that. Then you have what you call Px, the set of all subsets of X. And you see that Px in fact satisfies all these requirements. Okay. Then you can talk about various subsets of that. Let us designate by M, which is a subcollection of X, such that these three properties are satisfied. That is, X is a element of M. Then you have, if A belongs to M, then A complement belongs to M. Then you have third property, if An belongs, is a subcollection in M, countable subcollection, say N equal to 1, then union so what we demand is this: we choose a collection, a subcollection of P X with the property that the given set X is an element of M, and if A belongs to M, then A complement belongs to M. Then if An is a countable collection of subsets belonging to M, then their union also belongs to M. I mean, these three properties do not require any other structure of X. In fact, they are not using anything else other than just the basic theoretic properties like union, intersection, etc. Now, the immediate consequence is that you see that the empty set belongs to, that is because empty set is equal to complement. So by the second feature, that A belongs to M implies A complement belongs to M. We have X belonging to M, therefore X complement belongs to M. X complement is nothing but the empty set, therefore empty set is an element of, that's something that you conclude. Another thing that you can conclude is that okay, so we need one more. Yeah. Second thing is that intersection of 1 to n, 1 to infinity, an complement belongs to, or why is it so? Because an is an element of M, implies an complement is an element of M, and an complement is also in M. Therefore, you see that this can be written as, let us see this. So this is essentially equal to union 1 to infinity complete. See, union 1 to infinity an belongs to M implies union 1 to infinity an complement belongs to M, which is nothing but intersection 1 to infinity an complement. Therefore, that belongs to M. Or we shall write it in this way. Why this is just a proof that. So we shall write if an 1 to infinity is a subcollection of M, that implies and therefore you see that intersection of which is equal to, or I can write here, an which is equal to this, and you see that this belongs to M, therefore its complement an complement belongs to M, so you have this belonging to, so this is equal to what do you have, intersection so you see that this belongs to M, therefore its complement also belongs to M. Its complement it can be rewritten in this particular form, which means to see that intersection n equal to 1 to infinity n. Okay. So in particular, M is also closed under finite union and finite intersection. That's an easy inference. Intersection. That is because you see that choose etc. If each AK is belonging, contained in M, we have both these things, that is intersection, union. I can put this AK. And which is a finite union and finite intersection. Now this is equal to union 1 to n AK. Intersection so you see that this M with these three assumptions have the property that the given X belongs to M and A belongs to M implies A complement belongs to M. The collection AN has a feature that for each AN is an element of M, then their union is also an element of M. From this you can infer that the M contains the empty set. M is closed with respect to finite union. M is closed with respect to countable intersection. M is closed with respect to finite intersection. All these things can be inferred from that. So there are a lot of things that you can deduce from there. And then this M we call, see this M is like the Lebesgue measurable sets you have. If you recall the Lebesgue measurable sets, what do you have? You have it is closed under addition. I mean, it is the whole R is in it. It is closed under countable unions. It is closed under countable intersections, and all these features are there for it. Okay, an empty set is an element of that. So these features are there. It has much more rich structure coming out from the other properties that you want, which you cannot expect here unless you have more specific knowledge about what X is. We are assuming X to be. Now this M, this collection M with these features is called a sigma. Script M on of subsets of X. So what do we have? We have now two things. One, the set X with a sigma algebra on it. Okay. Thus we have with a collection of subsets, which we write like this, the pair xm, and M forms the conditions. And AN is a countable collection of subsets of M. Then this is what is called a sigma. In fact, you immediately see that the set of all subsets of X form a sigma algebra. Okay. So note that is a in fact this condition is not necessarily true. In fact, even if when X equal to empty set, Px consists of, now this is also a sigma algebra. So this condition is not necessarily required. Okay, but I just list it out. So this is something trivial situation that you have. On any X, X say, is a sigma algebra. Now there are, one can explore this, and on a given X there are several subcollection of So it's a variety of possibilities that is now open to you. You to have a given set on which you can choose a sigma algebra that is suited to your purpose. Okay. Now, for example, let us look at this problem. Very simple, another example. Take x to be 1, 2, 3. Now let us take the set of all subsets consists of, there are 8 elements in that you can list out and it forms a sigma algebra, but that is very trivial to see. What you have is, you can have another non-trivial sigma algebra. Suppose you take M to be set singleton 1, then its complement 2, 3, we can easily check that this M forms a sigma algebra. So this is a non-trivial sigma algebra. Okay, it's not Px, it's a subcollection of Px which forms a sigma algebra. You can easily check that all these conditions are satisfied. It's a finite collection of objects. Now, there are other subconnections that you can create and check they form a sigma algebra. And this is quite easy. Instead of 1, you take 2, and then its complement would be 1, 3, and then the same thing. And then if you take 3, you get 1, 2 as its complement. So for each set in M, its complement should be that is something required. Okay, so that's a example which is not like the one that we have seen, namely the real line. So the what we have done is very general. We are now looking at only subsets with a certain, and choose a collection with a certain structure, and that we call it sigma. So make a definition. A set X with a sigma algebra M is and we call elements of M sets. Okay, you recall our Lebesgue integration theory, which we had x equal to r, and then all Lebesgue measurable sets just constructed in through a very elaborate scheme, because we were specifically looking for A generalization or extending the concept of length to a larger class of sets in R, as large a class as possible on R, and this was constructed in a systematic way, and then we obtained what are called the Lebesgue measurable sets, and then X or R with the Lebesgue measurable sets was called the Lebesgue measurable space. Okay, so this is a measurable space. These elements are called measurable sets. Okay. So there it was very specific. We had a specific purpose. But here we have now generalized it by looking at the basic features of the Lebesgue measurable sets and avoiding anything that requires the specific structure of R. Okay. Now I'll just use this idea and then I'll just compare this possibly with a topological space. I mean, that's comparison is worthwhile. What is a topological space? X is and you call tau is a collection, is a subcollection, is a px, just like your script type. Okay, with the features, with the properties. One X and the empty set are elements of tau. 2 intersection k equal to 1 to n ai belongs to tau. That means tau is closed under finite intersections. The third condition that we have is that tau is closed under arbitrary. See, third problem is that an index set and A alpha belongs to X belongs to tau for every alpha belongs to lambda, then union that means arbitrary union of elements of tau belong to that, and we called A alpha or tau is called the collection of open sets. Once again, you compare with the real line on which we had the usual topology. Usual topology is something that comes from the distance metric that we define, that is d of then it's a metric space, and every metric space is a topological space, and you can define what are called neighborhoods of points, and using neighborhoods you can define what are called open sets, and those open sets have these particular properties, that it is closed under finite intersection and arbitrary union. Okay, so just compare these two now. Compare the two they are different, of course. Obviously, they are different. Okay, but there are some striking similarities that you also observe. Okay, so in both the cases you have x, and then you are playing around with a collection of subsets of x having a certain features. The feature that we make use of for measurable sets is the so-called what you call the measurable property, or a collection of sets with a certain structures. And then here again we define on that, you choose a collection of subsets, certain properties which we have listed out here, and they satisfy another set of conditions. And you call each element of tau an open set. Okay, so these are endowing x with certain structures to serve our purpose by picking up a collection of subsets having some specified property. Okay, and these elements of tau we call open sets. Elements of script m we call, that is the sigma algebra. The elements of the sigma algebra we call it measurable sets. Okay, so x, on one side you have x with a sigma algebra, on the other side you have x with a topology of it. Okay, so these two are, this comparison is probably worthwhile to see what follows from it. Now we will work with the concept of mappings from x to some spaces with certain structures. Once again, let us go back to the case of R. So you take So let me designate this. So let me take R with Lebesgue measurable sets. This is a measurable set. And we have R with the concept of distance. We write this tau coming from the this is the usual topological space, which is a metric space. Or we take this tau d consists of all the open sets that come out from a distance. They are at the outset comparable. Then what we do? We define functions from R. We also, so look at this functions. Okay. We also are familiar with G defined from R. That is from topological space R to the usual topological space R. That is, we are talking about real value functions. Then we defined G to be continuous if F inverse of P belongs to tau d for every V belonging to, so I write as tau d. Right. Okay. We defined G as continuous. What was our definition for measurability? Recall. Compare this. Defined F to be measurable. Lebesgue measurable provided F inverse of is measurable. So compare these two definitions. Okay, it is in script M, and here as it is our tau du itself. So this, in this case, we said F is measurable. Okay. So we are talking about what are called real valued functions. Okay. We are talking about real valued functions F from this is what. Now we can generalize this idea. Okay. Generalize it possibly in a most general form, and we have a, suppose you have two topological spaces. X let now you see both X and Y have a collection of subsets chosen to decide how near elements are in X and Y. Okay, right? That means you have topologies identified. Now F from, therefore we are now in a position to talk about whether nearby points in X gets mapped to nearby points in Y by F. Okay, or in other words, is F continuous? Is F continuous? That we have said is roughly speaking what we ask for is, does F map nearby points to that we suppose x1 and x2 are 2 points. So let us take the case of the distance. So they lie arbitrarily close to each other. Do they get mapped? That is fx1 and fx2 stay closer in y? This is the question that you are asking. Okay. So we say that this is the case. Or by use the terminology, f is continuous. F is continuous, provided that means you have this one. Take V here. V belonging to is a element of tau y. So this is an element of tau, and this, the pre-image of this, or the set of elements to which E gets mapped. Okay. So all those elements who under F gets mapped to, this is what we mean by inverse of P. F inverse of P is an element of tau x. And if this is true for every P belonging to tau y, then you say that F is. So that's the definition. Now, analogously, you have the concept of F measurable. What is it? F is measurable. So we have now X, M, and Y. I'm taking a general scenario. So I have mapped from, this is a measurable space, this is a topological space. Provided same sort of thing. F inverse of Y or F inverse of V belongs to M for every compare the two. See, the only place it differs is here. Instead of tau x, you have now. Then you say F is measurable. Then we say F is see, like the status of continuous functions you take, they play an important role in analysis. Similarly, measurable functions also have a very important role to play in analysis, especially in the development of integration. Okay, because why not some other structure? Well, one can put another measure space, another measurable space, and then you can, instead of topology, you can completely replace by measurable space. So that, of course, is not something that is useful, because later on, after all, we want to work with real valued functions or complex valued functions or vector valued functions, or even more general class of functions. And in all these cases, you see that the range is to be fitted with not an arbitrary set, a set to be fitted with some kind of topology, okay, to serve our purpose, develop the integration theory. Therefore, we would keep this as the definition of a measurable set. So, continuous functions do play an important role in the context of mappings from clean topological spaces. Measurable functions play an equally important role for mappings from what are called measurable space to topological spaces. I think I will just stop here and then continue with this in my next lecture. So thank you very much. So you have got an idea by this time how the generalization is taking place. Okay? How it is comparable with what we had on R. On R, you see, you have got the open sets which provide it with a topology. On R, we have measurable sets which provides it with the Lebesgue measurable class of subsets. Okay, makes it a measurable space in the sense of that. And here you see, you also observe that an open set is measurable, but its complement is also measurable. Whereas the complement of an open set is not a open set, right? See the difference. So the sigma algebra is totally different, is different from the usual topology that you have on the real line. Okay. All open sets are what we usually ask for, and what happens is that all open sets are Lebesgue question. Okay. But there are other sets which are also, okay, like all closed sets are measured, but all closed sets are not open sets, except the trivial situation X and phi, where or R and the empty set, which have the status of being an open set as well as a closed set. Okay, so I think with these remarks, let me leave, and then maybe I'll come back in my next lecture to go further. Okay, thank you very much.